These machines literally dictate almost every single aspect of our modern lives. So today, we're diving deep into the fundamental mechanics of computing. In this explainer, we're going to explore the brilliant physical anatomy and the absolutely astonishing historical evolution that brought us into this modern era.
Here is our roadmap for today. We're going to build our foundational knowledge in 3 simple steps. First up, what actually is a computer? Second, we'll look at the history of computing. And third, we'll break down understanding computer hardware.
All right, let's jump right into section 1. What is a computer?
At its absolute core, a computer is really just an electronic system that accepts data, processes instructions, and generates output information. It basically takes facts and figures, executes operations on them, and gives us a usable result. And the central processing unit, the CPU, acts as the absolute brain of the whole operation, handling all that complex logic that makes this entire thing possible.
To put that into perspective, let's think about the literal flow of data in action. First, you've got your input. That is the raw data entering the system. Then that data gets pulled straight into the central box, the CPU, where the control unit and the arithmetic and logic unit act as that brain we just talked about. Once the processing is done, the data flows right out as useful information. So input goes in, the brain does the heavy lifting, and practical output comes out. It's honestly an elegant, perfectly structured cycle.
Okay, moving on to section 2, the history of computing.
It is so fascinating to see how humans solve mathematical problems over a span of like 5,000 years. We start way back in 3000 BC with the abacus, just a simple mechanical device used by merchants for basic math. Fast forward a bit to the year 1642, and we get Blaise Pascal's mechanical calculating machine. Then, in 1804, Joseph Joccard totally revolutionized things with a loom operated by punch cards. People were literally feeding instructions into a machine to control it. But the real game changer hit in the 1830s with Charles Babbage. He's widely known as the father of the computer, and he conceptualized the analytical engine, a machine that could process an unbelievable 60 instructions per minute using those punch cards. Pretty wild, right?
But mechanical computing definitely had a ceiling. By 1937, IBM developed the Mark I. Now, this was a massive achievement for sure, but it faced some severe physical limitations. These early computers relied super heavily on physical moving parts, so their speed was limited by how fast those literal pieces of metal could move. And worse, they physically broke down from continuous wear and tear. Just imagine gears and levers constantly snapping mid-calculation. That physical frustration is exactly what pushed scientists away from mechanical devices and squarely toward electronic solutions.
18,000 vacuum tubes. That massive number represents the next great leap in 1943 with the ENIAC, a true electronic computer. To finally ditch those slow-moving parts, they used 18,000 vacuum tubes. This machine was an absolute behemoth built at the University of Pennsylvania. It took up 20 by 40 square feet of space. I mean, that's the size of a large room. But without those fragile mechanical parts holding it back, the ENIAC was wildly fast for its time. It was able to add numbers in just 200 microseconds. A total breakthrough.
Even with all that electronic speed, there was still one huge operational flaw. To change a program, you had to physically unplug and rewire the massive machine. It was a wildly difficult and tedious task. And that brings us to this major turning point, quote, by John von Neumann regarding the stored program concept. He proposed that data and instructions can actually be stored together internally in the machine's memory. Because of this brilliant idea, the computer could just pull instructions one by one automatically. No more manual rewiring. Honestly, this single concept is the bedrock of almost every single computer we use today.
Let's dive into section 3, understanding computer hardware.
So, what exactly is hardware? Simply put, it's the physical parts of a computer system that we can actually see and touch. Hardware is basically the collective term for all the physical components that execute the commands given to them by the software. And the absolute most important takeaway here is this. A computer literally has no existence or capability without these physical parts. They are the essential foundation. Sure, software provides the smart instructions, but hardware does the actual heavy physical lifting. To make sense of all these pieces, we divide hardware into 2 main categories, internal and external. You can think of internal hardware as the internal organs of the computer. They're hidden away inside the case doing all the critical background work, things like the CPU, the RAM, and the motherboard. External hardware, on the other hand, well, those are the peripheral devices connected on the outside. These are basically the limbs and the senses of the computer: the monitor, the mouse, the keyboard. You know, the parts we actually interact with day to day.
If we were to pop open a computer case, we'd see exactly what's powering our machines. You've got the main board or motherboard acting like a central nervous system connecting the whole shebang together. You've got your internal storage, like the hard drive, keeping your data safe, along with the RAM. And of course, you can't forget the power supply unit. Without that PSU, none of these incredible internal organs would have the electricity they need to actually function. Now, let's look at the external side, starting with common input devices, like keyboards, mice, and scanners. Remember that block diagram from earlier? Well, these are the physical tools that act as our human senses, communicating our intentions directly to the computer's brain. When you type on a keyboard or click a mouse, you're literally feeding alphanumeric data and control commands into the system. It is how we establish a connection and command the machine to do exactly what we want.
On the flip side of that, we have common output devices. If input devices are how we talk to the computer, output devices are how the computer talks back to us. The monitor is absolutely the most vital one, acting as the primary visual display so we can actually see the processed data. Add in printers for physical paper copies and speakers for audio output, and you've got a complete communication loop. We give the input, the internal hardware processes it, and the output devices deliver the final processed result straight to our human senses. It is truly amazing when you step back and look at the whole picture. I mean, we started this explainer looking at merchants using wooden abacuses 5,000 years ago. We then moved to a room-sized electronic machine with 18,000 vacuum tubes that originally had to be physically rewired just to change a basic program. And today, that entire cycle of input, central processing, and output happens billions of times a second on a tiny sliver of silicon sitting quietly on your pocket. The pace of this technological evolution is nothing short of staggering. So I'll leave you with this question to ponder. We went from 18,000 vacuum tubes to processors in our pockets. With the rapid rise of quantum computing and artificial intelligence, what will the next generation of computing look like?